Welcome to the first video of the third chapter. Let's again take a look at the PV system design overview. In week 2, you learned about the location-related aspects of PV system design, such as the meteorological data, surrounding landscape, and the plane of the array irradiance. In this part of the course, we will focus on the PV modules. This week, you will learn how modules are constructed from solar cells and how multiple modules form a PV array. We will discuss the state-of-the-art PV module structures, and you will learn how the interconnection of cells and modules affect their electrical properties. But first, let's take a look at the relevant properties of PV modules as found in a typical datasheet. This is the datasheet of a PV module by Panasonic based on heterojunction technology. The enlarged area indicates the dimensions and weight of the PV module. The dimensions of the PV module are important for PV system design in order to estimate the total irradiance incident on the module and the space required for the installation. Starting from the left-hand side, we have front side and back views of the PV module, including the frame and the junction box. The junction box is represented by the little square on top of the black view with the connectors attached to it. The weight of the module can be found underneath this figure. The weight can be an important property if the area on which the modules are installed has limited weight-bearing capacity. Below the dimension and the weight box, the warranty strategy can be found. The warranty varies depending on the module manufacturer. You can see, for example, that this module has a standard tiered warranty that warranties a power output of 90% of the minimum power output for the first 10 years. From year 10 to year 25, 80% of the minimum power output is warranted. Then, the various materials of which the module is composed of are listed. These materials include the heterojunction with the intrinsic thin layer solar cells, the anti-reflection coated glass, the black anodized aluminum frame, and the connectors. Finally, the certificates are listed, indicating that the module is up to the standards. You will learn more about these certificates later in the course. Another important module parameter is the irradiance dependence of the module. These are the voltage, current characteristics under different irradiance conditions and at constant module temperature of 25 degrees Celsius. Generally, a single light source is used to simulate the different irradiance level. The irradiance level is reduced through the use of filters. At a fixed temperature, the current increases with increasing irradiance, starting from more than 1 ampere at 200 watt per square meter to a value 5 times higher at 1000 watt per square meter. Finally, let's take a look at perhaps the most important part of the datasheet, the electrical data. These are organized into 4 groups. The first table provides the properties at standard test conditions. Next, the temperature characteristics are shown, followed by the module properties at normal operating conditions. Finally, the module performance under low irradiance conditions is shown. Let's start with the properties at the standard test conditions. As you may recall, the standard test conditions are 1 sun illumination, which is the AM 1.5 spectrum at 1000 watt per square meter, a constant module temperature of 25 degrees Celsius, and the absence of wind. However, under outdoor conditions, the modules are typically at a higher temperature than 25 degrees Celsius and at lower irradiance conditions. Therefore, the nominal operating cell temperature, or NOCT, of a PV module is provided in the datasheet. This NOCT is the temperature at which the module will operate when it is under open-circuited conditions, when the air temperature is 20 degrees Celsius, the AM 1.5 solar irradiance is equal to 800 watt per square meter, and the wind velocity is 1 meters per second. In this example, the NOCT is 44 degrees Celsius. Having defined both the STC and NOCT, let's focus on the electrical data of the module. The power, the voltage, and the current at the maximum power point, the open circuit voltage, and the short circuit current. For the STC, also the maximum current and system voltage are reported for safety reasons, as well as the production tolerance power. This last parameter specifies the range within which the PV module will either overperform or underperform with respect to its rated power at STC. The second table also provides temperature coefficients for the short circuit current, open circuit voltage, and maximum power. With these coefficients, the performance of the module can be evaluated when the module operates at temperatures other than the NOCT. In fact, as you can see, at the higher temperatures, the short circuit current is increased, but the voltage and maximum power are decreased. In summary, in this video, we discussed how to interpret a PV module datasheet. In the next video, you will learn more about the PV modules available in the market. That way, you will be able to select the best PV module for your PV system.